My journey started largely instrumenting code to run on a single GPU. This was state of the art when I started. And that was sort of great. We had some challenges, but we had this disk media called SATA, and it sort of kept up with what we wanted to do. But it didn't take long when we started instrumenting code for multi-GPU, particularly as science began to increase the size of data. We could do more, so they were doing more. So we were growing the platform capability by adding more GPUs, adding more sophisticated memory topologies. And eventually, we exceeded the capacity of a single node. We started scaling out across IP. Now, that's really interesting story because at some point, we had to deal with the fact that we were losing our capacity to generate higher data sets and process them timely, which is where we come to the story today called full stack innovation. Now, in my world, that really entails us bringing together CPU, GPU, networking, and storage across the backplane, both the north, south, and east-west backplane for the networking in order to generate value for our customers. And that still remains to be our story today. Myself, including everybody on the SA team's goal is to generate value using customer science. Well, that's real. So here we can talk about this, but we have to peel back a little bit over what we sort of showed you, which is the big placemat slide of what's capable. Is probably what you see in a lot of presentations, but I wanted to peel that back and really talk about the tools that we're using in order to do that. We have, of course, if you've been with us for a while, you saw the Kepler, you saw the Maxwells, and now, we sort of went through the Ampere and Hopper. And as we went through each one of these generations of GPU, some things happened that were really important, particularly for science. One, we got more compute cores. That's awesome. I'm a programmer. I want more compute cores. I want more capacity. I want higher clock frequencies on the CPU. And I also wanted more memory on that GPU. And so that's been growing as well. And as we go through Hopper, we go to Blackwell, which is which is available to us today. And ultimately into Rubin, the memory capacity of these GPUs is growing. And we wanted this because we were trying not to have to scale out of the node. And we largely achieved that for a good part of the science. But then this thing happens again where science starts increasing the size of the data sets because they can. There's capacity for it, there's capability for it, and there's a need for higher fidelity science. And so as we get into Blackwell, we have to use some really critical tools on our backplane. So we do have, of course, the great CPU. Fine, we have a CPU. I happen to like that CPU too. But we did some innovation on the network backplane, both for Spectrum X and Quantum IB, to give us really high performance lossless Ethernet. We also have NVLink 72, which strongly interconnects the rack. So now I can scale up the entire rack as a single compute node. And I got this question just this morning. Well, what can I do with an M.2 inside my node? And I said, nothing. You're gonna need a network compute stack that actually has a strong storage compute element. And we had these long conversations this morning around, what does it mean to actually disaggregate your compute and then take advantage of some like a DDN storage so that you can move away from 2 gigabytes per second up to 80 gigabytes per second per GPU in a node, all going out to a DDN storage system across our Ethernet fabric. And the story continues as we go across Rubin. That GPU only gets bigger, in case you're wondering. That GPU gets bigger, it gets faster, and it gets more capable. And in doing so, we actually open up a whole new branch of science, which is largely what's driving our need to build a better storage fabric. This is called physics AI. And you might have heard it called a PIN or a physics-informed neural net. You might have called it a Fourier network operator, FNO, or a GNO. There's all kinds of different instrumentations or models that we're building. But really, this fits solid within the HPC domain. And you're going to see more of it because these surrogate models allow us to collapse days, weeks, even in some cases, a year worth of compute into just days. By building surrogate models, we can compress complicated computations into a physics-based model that's trained with CUDA. It's trained with the GPU. It's trained with first principles math and physics. And it needs an enormous amount of data. It needs an enormous amount of compute, and it also needs a lot of data to do it. And so we see this sort of convergence between, and my colleagues can speak on this a little bit later around what's happening in the AI domain. Well, that's sliding back into the HPC domain. That's why you see so many of these clusters begin to look very similar. there are some differences between HPC and AI for sure. But in this world where we go from 100x in electrothermal cooling all the way through 10,000x in aerodynamic cooling across the automotive industry, by using our best practices in GPU compute, in networking, and in storage, we're able to unlock the full capability of what science has been looking for a decade. But we're a full stack company, which means that we're not only hardware, and I sort of showed you hardware, most of you know us for hardware, but we also participate a huge amount in the software stack. At this point, as we go from single GPU to multi-GPU, to full rack, to cluster scale, to data center scale reference architectures, the only way that's really possible is if we actually participate in the entire stack. One of the key elements that relates to storage is called Magnum IO. And Magnum IO gives us the ability to directly communicate from the GPU to the storage system, and bypassing a huge amount of overhead and it's using a protocol, whether it be IB based or Ethernet based or port based with RDMA support. We're now able to achieve an enormous amount of speed up on many of our applications. In some cases, as we saw earlier in the slides, we can get up to 48% improvement in snapshot and checkpoint efficiency going in and out of those external storages. And it sort of jumps to something like a 2x improvement in performance. You'll hear more about this as we go through, but this really has to do with that tight coupling, that innovation that's happening between NVIDIA and DDN, and our ability to bridge those two worlds together to unlock the value of science. We also have some really interesting software stacks that we tag on top of Magnum IO. You'll see it throughout our HPC SDK, which is our enablement of science within industry. That SDK comes, of course, with CUDA and a few other compilers, but it also comes through all of our library stack and our commitment through our CUDA-X frameworks to make sure that we're leveraging the best that we can do. Magnum IO is looking for IB, it's looking for an NVLink, it's looking for Sharp, it's looking for anything it could do to optimize the network topology to increase its ability to read and write from storage, getting you the maximum amount of value out of your IOPS. And I'll leave you with this. What I've really described to you is an ability for you to make decisions without going into code, which we could do. We could talk about how you best use our frameworks, but really these decisions is your goal to increase throughput. You have choices to make, and it's not going to be sitting back on slow storage. You're going to have to make some innovation in the full stack. It could be responsiveness, energy efficiency, cost and complexity. All of these come into play as we talk about HPC. And since HPC is now dragging in and encroaching in on the AI world with physics-informed neural nets, we have a few more decisions to make on how we build those high-performance clusters.